A brief introduction: concentrated photovoltaics, past to future. How diamond cooling could revive CPV, our thesis. Concentrating sunlight to make power is one of the oldest ideas in energy. In 1866, Augustin Mouchot built the first practical solar concentrator, using polished mirrors to boil water and drive a steam engine. In 1912, Frank Schumann ran a full-scale solar irrigation engine in Egypt, the direct ancestor of the concentrating solar plants operating today. The lens and the mirror have been with us for over 140 years. The photovoltaic cell is the newcomer. Concentrator photovoltaics, or CPV, uses lenses or mirrors to focus sunlight onto a small, expensive, high-efficiency solar cell instead of spreading cheap cells across a wide area. The promise was simple. A multi-junction gallium arsenide cell converts over 40% of sunlight into electricity, roughly double what a standard silicon panel does. Concentrate the light 1,000 times, and you only need 1/1000th as much cell material to gather the same energy. The cell is expensive, the optic is cheap. Concentration is the economic bridge between them. Between 2010 and 2015, CPV was the fastest scaling solar technology in the world. Amonix, Soitec, Suncor, and Solfocus raised over $1 billion in combined capital. Utilities in the American Southwest, Spain, South Africa, and China signed power purchase agreements. The International Energy Agency projected CPV would reach gigawatt scale by 2020. Then the industry collapsed. Between 2015 and 2018, the major CPV manufacturers shut down, sold, or pivoted. Amonix dissolved. Soitec exited solar. Solfocus had already folded. The projected gigawatts never materialized. The technology that was supposed to be the future of utility-scale solar became a footnote. The standard explanation is that silicon got cheaper faster than anyone projected. That is true. Silicon module prices fell roughly 80% between 2010 and 2017. CPV could not keep up. But that explanation is incomplete. It treats CPV as a victim of a price war it lost on cost per watt. The fuller diagnosis is that CPV lost a thermal war it was never engineered to win. A multi-junction concentrator cell operates under 1,000 times normal sunlight intensity. That means 100 watts of optical power focused onto a square centimeter of semiconductor. The cell converts roughly 40% of that light into electricity. The other 60% becomes heat, inside the cell, almost instantly. 60 watts of heat inside 1 square centimeter of gallium arsenide. The cell is less than 200 microns thick. The heat has almost nowhere to go. Without active removal, the cell temperature climbs toward 400 degrees Celsius in under 30 seconds. At that temperature, the semiconductor is destroyed. This is the first fact that determines everything about CPV. The better the cell, the more light it can usefully absorb, and the faster it dies from its own waste heat. The multi-junction cells that made CPV attractive in the first place are the same cells that make its thermal problem the most severe. The relationship between temperature and efficiency is not linear. It is a coefficient, measured in percent loss per degree Celsius. For a 4-junction cell, the efficiency drops roughly 0.04% for every degree above 25 Celsius. For a 6-junction cell, the coefficient is steeper, closer to 0.12% per degree. The more junctions, the more sensitive the cell is to heat. The cells that pushed the efficiency records were the most heat-vulnerable cells ever put into a concentrator. In legacy CPV architecture, the cell is bonded to a copper heat sink. Copper conducts heat well, around 400 watts per meter per Kelvin. But copper is dense, heavy, and expands aggressively when heated. The cooling system attached to that copper is the second cost. Active water pumping, microchannel cold plates, radiator assemblies, and structural supports to carry the load. A 1 kilowatt legacy receiver cluster, with its copper cold plate, coolant, piping, radiator, and supports, weighs roughly 8 kilograms. That mass sits at the focal point of a dual-axis tracker that has to follow the sun to within 1/10 of a degree. Heavy receivers require heavy trackers. Heavy trackers require large motors, thick structural steel, and deep concrete foundations. The thermal problem at the cell propagates outward, through the receiver, through the tracker, through the mounting structure, all the way to the cubic yards of concrete poured into the desert. This is the cooling tax. It is the reason CPV could not win a cost war against silicon, even with a cell that was twice as efficient. The cell was cheap enough. The optic was cheap enough. The structure required to keep the cell alive was not. The solution to the thermal problem at the cell has existed for over 30 years. It was not developed for solar. It was developed for lasers. A high-power laser diode has the same problem as a concentrator solar cell. A small semiconductor die, generating intense heat, bonded to a heat spreader with almost no margin for temperature rise. If the die gets too hot, the laser fails. The same physics, the same geometry, a different industry. Since the mid-1990s, laser diode manufacturers have bonded synthetic diamond heat spreaders directly to the back of their chips. Diamond conducts heat at roughly 2,000 watts per meter per Kelvin, 5 times better than copper. The heat leaves the die immediately, spreads laterally across the diamond, and enters the downstream cooling structure at a lower temperature and a wider area. Element 6, the synthetic diamond arm of De Beers, has sold thermal-grade chemical vapor deposition diamond wafers for laser diode and high-power electronics packaging for roughly 3 decades. The bonding chemistry, the surface preparation, the interface engineering, these are solved problems in the laser and RF industries. They are not new science. The reason this solution was never applied to concentrator solar cells is cost. A diamond heat spreader for a laser diode might sell for thousands of dollars per square centimeter. A laser diode sells for thousands of dollars. The diamond is a small fraction of the device cost. A concentrator solar cell, even a high-efficiency one, competes against silicon at cents per watt. Putting a $1,000 wafer under a solar cell was never economically rational. The physics worked. The economics did not. Nothing about the thermal problem of CPV required a new material discovery. The material was known. The bonding was known. The performance was known. The only thing missing was a price at which it made sense to take a 30-year-old solution from the laser industry and put it under a solar cell. The price arrived, but not because of solar. Beginning in 2023, the demand for high-performance thermal management in artificial intelligence data centers began scaling at a rate the synthetic diamond industry had never seen. The latest AI accelerator chips dissipate between 700 and 1,000 watts each. The generation after that, expected by 2028, will dissipate over 1,200 watts. The thermal management budget for a single high-end AI data center now runs into the hundreds of millions of dollars. The companies buying these chips will pay almost any price for a component that lets the chip run at full speed, instead of throttling to half its rated performance because it got too hot. This demand is bending the cost curve for chemical vapor deposition diamond. The capital flowing into AI thermal infrastructure is funding new reactors, larger wafer formats, faster growth rates, and automated processing. The equipment is expensive, but once it is built and paid for by the AI industry, it produces diamond for every other industry at a lower unit cost. This is the subsidy mechanism, and it is the core economic argument of this video. Solar does not compete with AI for diamond manufacturing capacity. As of 2026, roughly 82% of new diamond reactor capacity coming online is pre-allocated to AI accelerators, RF electronics, and defense through long-term supply agreements. Solar has access to perhaps 8 to 12% of the remaining merchant capacity. But solar does not need to win the capacity battle. It needs the cost curve to come down. And the cost curve comes down because the AI industry is paying for the infrastructure that makes diamond cheap for everyone. The trajectory is measurable. In 2024, thermal-grade polycrystalline diamond cost roughly $5,000 per square centimeter in low-volume custom research orders. By 2026, early AI thermal spreader deployments brought that figure toward 2,600. By 2029, mass-scale 915 MHz plasma reactors are projected to bring it under 1,000. By 2033, automated volume manufacturing on 6 and 8-inch wafer formats is projected to reach a floor between $110 and $135 per square centimeter. That is the crossover. At $120 per square centimeter, a diamond heat spreader under a concentrator solar cell is no longer absurd. A 1mm cell, the kind used in micro CPV architectures, needs a diamond backing of perhaps 100 to 200 square millimeters. At $120 per square centimeter, that is between $1.20 and $2.40 of diamond per cell. The cell itself, the multi-junction semiconductor, costs several dollars. The diamond is no longer the dominant cost. It is a thermal component, priced like a thermal component. This is the argument, stated plainly. Diamond did not invent a new way to cool concentrator solar cells. The way it cools them was invented in the 1990s for lasers by other people, for a different industry. What changed is that the AI thermal boom bent the diamond cost curve far enough, fast enough, that a 30-year-old solution finally became affordable to put under a solar cell. The innovation is not the physics. The innovation is recognizing the moment when the cost curve crossed the point where borrowing that physics becomes the cheapest way to keep a concentrator cell alive. There is a parallel worth naming. In 1856, Henry Bessemer did not invent steel. Steel existed. He invented a process that made steel cheap enough to build railroads and skyscrapers. The Bessemer moment was a manufacturing crossover, not a material discovery. What is happening with diamond is the same shape of event. The material existed. The cost made it irrelevant to most industries. The manufacturing scale changed the cost. The industries that could never afford it before can now begin to afford it. The solar industry does not need to fund the reactor construction. It does not need to win capacity allocation. It needs to watch the price per square centimeter, and when it crosses the threshold where the diamond backing is a small fraction of the receiver cost, the thermal wall that killed CPV in 2015 becomes a solved problem using borrowed physics, paid for by someone else's capital. The cost trajectory is not speculation. It mirrors the scaling curves seen in silicon wafer manufacturing, in LED substrate scaling, and in every other semiconductor material that moved from custom research product to volume commodity. The floor is set by reactor throughput, wafer area, and process automation. Each of those is being pushed upward by the AI industry right now. The floor falls on a schedule that is visible in the capital expenditure announcements of the diamond manufacturers, not in the hopes of the solar industry. Act 5. The bankability case. Affordable is necessary but not sufficient. A concentrator solar installation is a 25-year capital asset. The bond between the diamond and the semiconductor has to survive 25 years of daily thermal cycling in a desert environment, or no project financier will fund the build. The structural problem at the interface is thermal expansion mismatch. Every material expands when heated. If the diamond and the cell expand at different rates, the bond between them is sheared twice a day, once when the sun rises and the cell heats up, and once when the sun sets and the cell cools down. Over 25 years, that is over 18,000 cycles. If the bond fails, the cell loses its thermal path and overheats. The legacy thermal architecture bonded the cell to copper. Copper expands at 17 parts per million per degree Celsius. The gallium arsenide cell expands at roughly 6. That is a mismatch of 11 parts per million. When the assembly cools, the copper contracts more than the semiconductor, pulling the cell into tension. Gallium arsenide is brittle in tension. The tensile stress caused gridline microcracking and, in severe cases, instantaneous fracture of the cell edges. This was a documented failure mode of legacy CPV receivers. Diamond expands at roughly 1 part per million per degree Celsius. The mismatch between diamond and gallium arsenide is about 4.5 parts per million, less than half the copper mismatch. But the more important difference is the direction. Diamond expands less than the semiconductor. When the assembly heats up, the cell is placed in compression, not tension. The compressive yield strength of gallium arsenide is roughly 10 times its tensile fracture limit. The diamond interface is structurally more robust, not just thermally more conductive, because it loads the cell in the direction the material can survive. The bonding method matters as much as the material. Surface-activated bonding, which creates an atomic-level join between diamond and semiconductor at room temperature, offers the highest thermal performance with thermal boundary conductance above 100 megawatts per square meter per Kelvin. But it is rigid. The localized shear stress at the die corners can exceed 350 megapascals during thermal cycling, which can peel the cell edges. The solution is a compliant interlayer, sintered silver nanopaste with a porous structure and a low elastic modulus, deforms plastically under shear strain, absorbing the mismatch without transferring destructive stress to the cell. It is the bonding chemistry that balances thermal performance with mechanical durability over thousands of cycles. The National Renewable Energy Laboratory subjects concentrator modules to an accelerated life cycle test of 2,500 thermal cycles from -40 to 110 degrees Celsius. Using a modified Coffin-Manson fatigue relationship with a fatigue exponent of 2.3 for sintered metal-bonded semiconductor interfaces, the lab cycle maps to a field cycle that is roughly 12.5 times less severe. 2,500 lab cycles translate to over 31,000 field equivalent cycles. A 25-year desert deployment involves roughly 9,100 diurnal thermal cycles. The accelerated test delivers over 3 times the required field exposure, providing the safety margin that institutional project finance requires before funding a 25-year asset. This is the bankability case. The diamond bond is not a laboratory curiosity. It is a bond whose failure modes are identified, whose mitigation chemistry is selected, and whose cycle life has been measured against a published fatigue model and found to exceed the service requirement with margin. The cost and the reliability make the diamond-backed receiver affordable and durable. The mass reduction makes the rest of the system cheaper. A legacy 1 kilowatt receiver cluster with its copper cold plate, liquid coolant, piping, radiator, pump, and structural supports weighs roughly 8 kilograms. A diamond-backed receiver with a 500-micron polycrystalline diamond wafer bonded directly to the cells and a compact passive aluminum pin-fin heatsink weighs roughly 665 grams. That is over 90% mass reduction at the receiver head. The mass does not disappear. It cascades. A 50-kilowatt utility tracker array that carried 400 kilograms of receiver mass now carries 33. The dynamic torque requirement on the tracking motors drops by over 70%, which allows designers to replace precision industrial gear drives with standard commercial tracking motors. The structural steel gauge needed to resist when load bending moments on the dual-axis boom drops by roughly 45%. The concrete foundation volume and pier depth drop by roughly 35%. Every one of these reductions is a cost reduction. The tracker motors, the structural steel, the concrete, the installation labor, the shipping weight, all of it gets cheaper when the receiver head gets lighter. The thermal problem at the cell was never just a problem at the cell. It was the root cause of the mass, and the mass was the root cause of the structural cost, and the structural cost was the reason CPV could not beat silicon even with a cell that was twice as efficient. The diamond backing does not just cool the cell. It unwinds the entire cost cascade that the thermal wall created. The receiver gets lighter, the tracker gets cheaper, the steel gets thinner, the foundation gets smaller, the installation gets faster. The levelized cost of energy, the number that determines whether a project gets built, comes down at every level of the bill of materials, not just at the cell. Every one of these reductions is a cost reduction. The tracker motors, the structural steel, the concrete, the installation labor, the shipping weight, all of it gets cheaper when the receiver head gets lighter. The thermal problem at the cell was never just a problem at the cell. It was the root cause of the mass, and the mass was the root cause of the structural cost, and the structural cost was the reason CPV could not beat silicon even with a cell that was twice as efficient. The diamond backing does not just cool the cell, It unwinds the entire cost cascade that the thermal wall created. The receiver gets lighter. The tracker gets cheaper. The steel gets thinner. The foundation gets smaller. The installation gets faster. The levelized cost of energy, the number that determines whether a project gets built, comes down at every level of the bill of materials, not just at the cell. Act 7. The 2033 crossover. The question that determines whether diamond-backed CPV is built is not whether the physics works. The physics works and has worked for 30 years. The question is when the levelized cost of energy crosses the cost of the alternative. In high direct normal irradiance desert environments, the Mojave, the Atacama, the Negev, the Arabian Peninsula, the economic comparison is not against average solar. It is against the cheapest available solar, which is single-axis tracked silicon. Silicon in those regions has already reached a levelized cost of energy between 2 and 3 cents per kilowatt-hour. CPV competes against that number. The diamond-backed micro-CPV architecture does not compete by being cheaper per watt of installed capacity. It competes by producing more energy per watt of installed capacity because the multi-junction cell maintains its efficiency at higher concentration and higher temperature than silicon can, and because the reduced tracking precision requirement lowers the balance of system cost. The combination of higher energy yield and lower structural cost closes the gap. The crossover, based on the projected diamond cost trajectory reaching the $120 per square centimeter floor by 2033, and the corresponding mass cascade savings on the balance of system, places diamond-backed micro-CPV at levelized cost parity with tracked silicon in high desert irradiance within the early 2030s. Not globally, not in every market, in the specific geography where concentration is most valuable and where the tracking tolerance advantage is largest. This is a narrow thesis. It does not claim diamond CPV replaces silicon. It claims that in the highest irradiance deserts on Earth, where the energy yield per acre is highest, and where the cooling tax has historically been most punishing, the combination of a borrowed thermal solution, a cost curve bent by another industry, and a mass cascade that shrinks the balance of system crosses the levelized cost of tracked silicon within the early part of the next decade. That is the crossover. That is the moment the thermal wall stops being a wall. ACT 8. The long view. Concentrating sunlight to make power is one of the oldest ideas in energy. Mouchot proved it in 1866. Schumann scaled it in 1912. The thermal concentrator, the mirror, and the boiler has been economically viable for over a century. What was never viable was concentrating sunlight onto a cell. The cell was the fragile, expensive newcomer, and the heat it generated inside itself was the thing that kept killing it. The cell is still fragile. The heat is still intense. The physics did not change. What changed is that the industry that cools the most expensive chips in the world, the AI data center, built the manufacturing infrastructure to make diamond cheap enough to cool the cheapest cells in the world. The laser industry proved the bond in the 1990s. The AI industry bent the cost curve in the 2020s. Solar inherits both. The diamond does not add energy. A lens concentrates light. It does not create photons. The power into the aperture is fixed by the aperture and the sun. The diamond backing, under the cell, does one thing. It removes the heat that the cell generates, fast enough that the cell survives and maintains its efficiency. That is all it does. But that is the one thing that, missing for 30 years, kept concentrator photovoltaics from being affordable enough to compete. The thermal wall that collapsed CPV between 2015 and 2018 was not a failure of the cell. It was not a failure of the optic. It was the absence of an affordable thermal bridge between a very hot, very small, very efficient semiconductor and a very cheap, very large, very cool sky. That bridge now exists. It was built by other industries, for other reasons, and it costs less every year. The lens is old. The mirror is older. The cell is the newcomer. The diamond is the bridge that finally lets the newcomer survive the intensity it was always designed for.